Okay, hello and welcome everybody. Please forgive my mask, but I'm in a shared office space, so I do have to wear it. I would like to, first of all, thank the invited speakers, Kainan Eng, Dylan Amir, and David Emiliore for joining us today on such a very short notice. So this event was scheduled only just over a week ago. And today we are going to talk about the technology, which, although it's not yet well understood in Earth observation research community, it's one of the new emerging technologies in AI community. And it has a very huge promise of being the one of the drivers of the next AI revolution. But with that part, I'm going to leave that to the speakers. And the aim of this session is for the Earth observation research community to better understand the technology, the sensors, and the processing units in order to establish whether there are any promising areas of Earth observation where it could be successfully deployed, giving us possibly a new way of solving the old problems. And we still have some people joining in, so I'm going to wait 2 more minutes before I'm going to pass the virtual floor to Kainan Eng, who's joining us from Zurich, I believe, and who is a co-founder and CEO of Innovation, as well as being a member in a variety of roles in other Zurich startups which deal with neuroscience, technology, and human-computer interactions, and as well as some teaching at ETH, I believe. Okay. Right. I think we can start. So this session is recorded. Unfortunately, we have a couple of different sessions which happen in parallel, so a lot of the attendees could not join us, but they will be able to watch this session later on. Okay. Please, Kainan, if you could start.
Okay. Do you hear me? Okay. Yeah. So thanks very much for the invitation. And glad we could get this session together at the last minute. Really excited to be able to present before the Earth observation community. So as Andre mentioned, I'm a co-founder and CEO of Innovation, which is a startup based in Zurich. I'll give a little bit of introduction to the company in this talk and a very brief introduction to the technical background behind the sensor technology, and then a look at how we've been dealing with some applications of this technology, and then how it can map, how we think it could map onto some space applications. Of course, the whole idea of this session, I think, is to start the conversation. Obviously, you guys will have ideas that we haven't thought of yet, right? We're not coming from the domain. So I'm really looking forward to kicking off this exchange. Okay, so just a little bit about the company. What we do essentially is high performance machine vision solutions. So this basically means attacking vision problems which are hard to do using existing technologies, either because they're too slow to respond, or they're not energy or compute efficient enough, or they're too big. And this, of course, is a sort of a very broad mission for the company. We founded in 2015, actually incubated for a couple of years before that, spin-off of University in Zurich and ETH. We have about 300 customers so far, all over the world. I'm glad to say.
Sorry, Kainan, to stop you, but we can't see your slides. I'm not sure if you're sharing them on or not.
Sorry, I forgot. Okay. Is that good?
Yes, thank you.
Okay, sorry about that.
And also to the attendees, if you have any questions to the presenters, you can write them in Q&A or in the chat, and we will address them later.
Yeah, so as I was saying, we've managed to deploy our technology to many countries, many customers over the past couple of years. And now that it's starting to get towards volume commercial applications, we've won a couple of different awards that you can see below. So I'll give a little bit of an overview of the technology. Basically, what we're talking about is a new type of vision sensor and also new types of processing architectures for dealing with the information from the sensor. So as you know, ever since photography was first invented, we deal with motion by taking a picture, then we take another picture, then we look at what's changed between those two pictures, and then we do this again. And there's a lot of redundant information, of course, which is basically wasted computation. Other disadvantages are that you have to wait for that next frame to be exposed. You have a fixed exposure time for the whole frame. And because of this fixed exposure time, you also have limitations with your dynamic range of your sensor. The research that led to the dynamic vision sensor, which we are pushing, started off as research into how human retinas perceive the world, right? Your eye doesn't take pictures. The cells are actually responding independently to the incoming light. And there's a pathway where every cell, or let's say every pixel, is responding only to the changes in illumination. And these are relative changes to illumination. So basically, every pixel in this new chip is operating asynchronously, independently of the other pixels. And so you get a very sparse data stream. Here you can see Toby, he's the inventor of the sensor, professor at the university, playing tennis. And the green pixels here are where that pixel became brighter within the last certain time window, and the red ones are where that pixel became darker. And so you're getting this sparse data stream of events coming off the chip. And so if you have the right way of processing these events, you can respond much faster to what's going on in the scene, and also with much less compute or power consumption requirements. Because the changes are also relative, you can get sensors with much higher effective dynamic range than you can get with normal sensors as well.
Sorry to interrupt you again, but it's been suggested to me that you should put your presentation in a slide show view so that it is bigger, if that's possible.
I'm doing
if you
that.
go to view and
do you see that? The thing is, my desktop is let me see if I can hide that menu bar at the side. Is that okay?
I think that's worse, actually. Sorry.
Yeah, let's go back to how it was.
Okay.
Before. Is that okay?
Yeah, it is better.
Okay. Yeah, the problem is I have this dual screen thing and it gets confused. Okay. So as I was saying, this is a very high-level overview of what's happening inside the pixel. So on the left-hand side, you have the photoreceptor. There's a photodiode. This is the same as what you have in normal image sensors. What's happening, though, is that the incoming light is being compared continuously in analog with a reference voltage, a threshold that's been stored. And there are two thresholds. There's one for when the pixel gets brighter and another one for when the pixel gets darker. And so basically, if the incoming light doesn't change by more than a certain percentage, then you get no data out of that pixel. And as soon as it hits the threshold, you get a digital event, so an on event if it's getting brighter, or an off event if it's getting darker. And then the threshold resets to the new value. And so this means that basically there's a mini circuit, about 40 transistors inside every pixel in the array. And then these events are read out digitally. There are different ways of doing this readout. which we don't need to go into here. Now, there's another variation on this circuit, which I'm not going to go into, but what you should basically see here is that the red part is what you saw in the previous slide. These are the events. That's the DVS part. Right in the center here is the photodiode, and down here is the photodiode. And what happens in the blue section is that you can actually read out frames in parallel with the events. So using the same photodiode, you can actually get events and frames in parallel. And this is what we call DAVIS. So DAVIS means DVS, so dynamic vision sensor, plus APS, active pixel sensor. So using the same sensor, you can actually get frames and events so that you can use both your existing processing algorithms and also this new way of processing your data. Again, some applications use both, some only use one or the other. Now, on top of this, we've constructed a layer which we call the dynamic vision platform. And this basically consists of the hardware, so the sensors themselves, the modules. We have reference cameras that people can use in their applications. Then we have this software platform, which takes care of all the interfacing to the cameras, deals with moving data around, and allows you to write different modules. I'll come back to this in a little bit in a subsequent slide. Going back to the sensors, so we've produced many sensors over the years, both when we were doing the research originally and also now in the company. These are basically, as you would expect, increased in resolution. The pixel sizes have decreased. It's always been a challenge to have as small pixel as possible while still maintaining good performance. We have ones which do just the events, some which do the frames and the events. We have color versions of this as well. In our latest prototypes, we have versions that can even do noise filtering and first level computation actually inside the array itself. Now, to go for the very large mass markets, such as mobile phones and so on, what we did was we entered into a partnership with Samsung. And so together with Samsung, we have the first sensors now at mass production. That's this so-called DV Explorer camera here. That's our development kit camera using this sensor. And of course, this is now progressing further into higher resolutions and even smaller pixel sizes in future. Now, coming back to the software, I'll just show one slide about how this works. Basically, this is a way to enable you to design your system as quickly as possible without having to learn all the intricacies of the circuits underneath, while still extracting maximum performance. So we have a high performance runtime written in C++. This is open source. That's the blue box here at the bottom. Now, to configure what's going on in that runtime, we provide this graphical interface on the left-hand side. This is, you can think of it a bit like Simulink or something. Each of these boxes here is a module. We provide a library of modules, and you can write your own modules. For example, the one at the top here is a camera interface module. The one at the bottom is a output display module. There are noise filtering modules, integration modules, and so on. And the different colors are different data types that you can use to connect these boxes. You can also define your own data types. So it's a fully open architecture, which allows you to build your applications as quickly and as easily as possible. We, of course, have bindings to other development environments. For example, we have connections to ROS, to Python, also to third-party frame-based cameras. On the right-hand side, you can see an example of real-time viewing of the output that's being produced by the engine. So in this case, you see some events, then some different types of processing. This camera has an accelerometer on it, so it's showing the output from the accelerometer as well. And so once you've completed your application and want to run it fully embedded, you can basically cut this line here and remove the graphical interface and just have your very efficient runtime running on your target platform. so that's the end of the sort of brief technical introduction. So the question is, what have we been doing, with this technology? And the way we approached this was we made the technology accessible to as many people as possible. This means to date over 300 customers all over the world. It started off as universities, as you would expect, and then has moved more and more into industries. Aerospace is a significant part of our customer base because that's an industry in general that has hard, high performance vision problems. So as you can see, it's many places in the US, Canada, all over Europe, some in the Middle East as well, one in South America. A lot is happening now in China, and of course in Australia and Japan. Basically all the rich countries in the world is now adopting this technology. Now, the use cases that people are working on are very broad. For example, we're engaged with development projects with car companies for autonomous driving and also for in-cabin observation of people. We're involved in industrial vision, in aerospace projects, as I mentioned. I'll just highlight two examples where I'm basically allowed to talk about what's going on. Now, the first one is in high-speed 3D laser scanning. Because the sensor is so fast, you can imagine that if you have the sensor and you pulse a laser, it can pick up this pulse very fast, and you can have extremely fast scan rates and very low latency on your extracted 2D contour. So in this product, we've produced a laser scanner which can produce output at 5 kilohertz, and with basically much lower latency than what is possible with normal laser scanners, and with the same level of accuracy that you can get with a normal laser scanner. So here you can see an example where it's scanning a little Lego man. I don't know if you can see, but you can actually make out the outline of the face of the person, of the Lego man. This basically shows you can tell the difference in the layer of paint that's on the Lego man. So it's pretty accurate. This is just a little video of the right. So we're working with a number of industrial automation partners on bringing this to the market in different use cases such as gluing, welding, and so on. Another use case I can highlight is in eye tracking. The idea here is basically in virtual reality headsets, which I'm sure you're all familiar with, right? You have to render extremely detailed, very wide field of view graphical scenes. And this requires a lot of GPU compute. Now, if you could track where the person is looking, that means you would only have to render in maximum detail where that person is actually attending to the scene. And the faster you can work out where they're looking, the more accurately and with a lower latency, the less compute you need to use to give the person the illusion that you're actually rendering the whole scene at full resolution with a maximum compute. And so what we've done using the sensor is produced an eye tracker that can track your eyes at 1 kilohertz with only 3 milliseconds of latency. That is also suitable for integrating into a mobile headset. I'll just play this little mini video down here to give you an idea of the pupil extraction going on. Right, so this thing's working at very low latency, very high update rates, and we're working with a couple of VR headset manufacturers on bringing this to market as well. So we're expecting this will become a default kind of technology in future VR headsets where battery life and compute is a concern. Okay, so now I'll move on to let's call it a more speculative part of the talk, where I'll talk a little bit about what we've seen some of our partners doing in space applications or applications related to space. Now, the first one you may have heard about, it's basically simultaneous localization and mapping. Because the sensor is so fast, you can imagine that it could be used for localizing things like drones, autonomous vehicles with much lower latency than is otherwise possible. And so one of our partners is actually up the road from us. He's from the same institute. Davide Scaramuzzo is professor at the university. And he's one of the leaders in doing work with drones. And what you can see here is an example of an application. Yep. Can you hear that noise? Should I try and switch off the audio?
I don't hear it, so I'm not sure about the other users, but
Okay.
there's no audio.
Okay, in that case, that's good. I'll just keep it playing then. So what you should watch in this little video is on the left-hand picture here in the bottom left, you get what the frames of what the camera is looking at. There's a camera looking down at the textured carpet. In the right-hand one, you get the events, what the DVS is seeing. And then in the middle, you get a reconstruction of combining this information into event frames. And that's what's being used to do the localization of the drone. In the bottom right-hand corner, you see the trajectory that's reconstructed. And so you can see in normal lighting conditions, it's able to use both data sources to get good data. When you switch off the light, suddenly you see that there are no more standard frames. It's too dark, right? It can't get a good exposure of what's going on. But because of the high dynamic range and good low light performance of the sensor, it's able to still extract the events. These are basically caused by edges, corners in the scene. And so the drone is still able to localize itself, even though the lighting has become much more challenging. So this is a kind of visual data fusion, you could call it, combining events and frames to get this robust performance. And then when you switch on the light again, it continues to work. Okay. So obviously, I guess, positioning satellites in space, you track stars, right? And star tracking, of course, is a big issue. This is, one example of a star tracker from a company which is being deployed on CubeSats. And so what we are guessing is that this could be a way to basically really reduce the amount of data that you need to pump into the star tracking system to be able to get your result out. And this will both reduce the amount of power that you need to spend on your satellite to do this positioning while maintaining the same accuracy, and also allow the satellite to perform more aggressive maneuvers because it will be able to respond faster. I mean, this is probably not really much of a topic, I think, in current space navigation, but we expect that as time goes on, being able to do more aggressive maneuvers like you see with drones will one day become a topic in space-based navigation. One of our chips, a set of our chips is going up on the first, I think one of the SpaceX launches next year. And this is basically just a technology validation launch just to check that it works at all. It was scheduled to go up this year, but then all this COVID stuff occurred. And I think at the moment it's booked in to go up next year. And that's with one of our collaborators in Sydney. Okay, so now I'll switch to ground-based observation. So here, one of our founders, the Professor Toby Delbrook, did a collaboration with an observatory, a network of observatories actually based in Poland. And what they wanted to know was basically how does this compare with conventional high-performance frame-based sensors? And so they took one of our high sensitivity chips. It's actually still a prototype. This one has backside illumination. At the time, there were not many sensors that did this. So that's why it's on a larger board there. And so as a first test, they just wanted to see, can we track a satellite going past at nighttime? And of course, the answer was yes. And by filtering out the noise with a simple data, you could basically get the track in real time with very low latency, quite simply, right? With very little data. So that was a first test. Now, then they moved on to another test, which was basically comparing this Davis sensor, that's the red part here, with a high performance image sensor normally used for astronomy. This is a frame-based sensor. And so they basically tracked at different speeds, so there's different speeds, and found that essentially the sensitivity of this prototype was not up to the level of the frame-based sensor. That was kind of to be expected. And so we think it's basically going to be a straightforward thing to close the gap. You just basically have larger pixels, you use more modern manufacturing techniques, and so on. But basically, we saw that the magnitude of stars that you'll be able to resolve using this sensor, there's no reason why it can't be similar to normal astronomical sensors. And the advantages were firstly, of course, that you're able to get your data much faster, right? The delay in getting your data is in the order of milliseconds, right? You don't have to do long exposures with complicated tracking and so on. And of course, the amount of data you have to deal with is much less. And so I think this is sort of one of the first signs of there being potentially a use case here for Earth-bound observation. Now, this is being sort of pushed a bit further, and then I asked the question, okay, we can do this at night, but we sort of expected that we can do this at night. And so can we do this during the daytime? And so they did a first preliminary test using a different kind of sensor chip. This is a different prototype. Now, normally with the DVS that we've constructed so far, the sensitivity for these change events is about 15%. That means that the light needs to change by about 15% for an event to be triggered. And this is actually fine for dealing with almost any situation on Earth, right, for sort of real world navigation recognition problems. Now, to deal with very faint objects in space, you need higher sensitivity. And so we have a higher sensitivity version of the Davis, which can respond to 3% changes in illumination. And so what they did was basically a daytime test. So this was at noon in Northern Europe, looking up at the blue sky just to see if they could distinguish a star, in this case, Vega, sorry. And they found that they were able to do this. So this was a first indication that it should be actually possible to track objects, to start with stars and then probably satellites and other objects during the daytime. Now, this concept has been taken much further with our collaborators at Western Sydney University. This is the group which Greg Cohen is running. I don't know if some of the astronomy community has heard about this, but he's developed this concept which he's called AstroSight. Right, and the idea is to use this type of technology to enable both daytime and nighttime tracking. They're focusing on tracking of space junk. That's the use case they've chosen. And they've created this concept of having basically a mobile network of telescopes which fit in a shipping container. So the container contains the telescope, which pops out above the roof of the container. All the compute is inside. And the idea here is that because the DVS is able to register itself and calibrate itself very quickly, that this could open up new opportunities for having distributed networks of easy to transport telescopes which don't require super elaborate configuration protocols. But yes, I'm not the expert of this, of course. So for further information, I strongly encourage you to contact the group of Greg Cohen at Western Sydney University. Okay, so that's basically the end of my short talk on this. I'm happy to discuss any ideas you have. Just please contact me. If you have any questions now, I'll do my best to answer them. But of course, please understand that I'm not an astronomy expert by any means. But anyway, thanks a lot for your attention and happy to take questions. Thanks.
Thank you very much. That was very enlightening. I don't get any questions. I didn't get any questions yet, so I think we can move to the next speaker, and we'll have the Q&A session at the very end. So our next speaker is Davide Migliore from Prophecy, who is going to tell us more about the DBS technology.
Let me see. Wait 1 second. Can you hear me?
Yes, I can hear you well. I cannot see your presentation yet.
Yeah, I'm sharing now. It's quite complicated to see the control of the presentation. So
Okay.
you see full screen?
Yes, it is full screen. Thank you.
Okay, so nice to meet you. I'm Davide Migliore, and I introduced before my company. I saw that Canon already introduced the technology, so I will not go into the detail of the technology to not overlap. The basics are always the same. I can say that my company started to work on one of the prototype coming from Zurich in 2010, and we started to create the full business here in France. We are located in Paris now. In 2014, we created the company with the idea to bring the technology from health application, neuromorphic community to the market. And particularly, the original idea was to enter in the automotive market. And then after, we wanted to try different applications, for example, in industrial automation or Internet of Things and so on. And now, after 6 years that we are working on the device, so prototyping and so on, we have several products, and we have a lot of collaboration, very interesting, that I will talk about. At the moment, we have a lot of patents. We are more or less 100 people that are working more both in hardware and software side. We are also doing algorithm, so we are also doing final solution. And we have office in US, Europe, Japan, and China, and several collaboration with many companies and the reseller. So now you can buy the sensor from different reseller, for example, Macnica in US, or in Europe now there is a collaboration with Framos that is creating the camera with our sensor. The products that are available on the market now are clear. It's already more than 1 year that we are selling this sensor. You can buy the chip to create your camera. So we have a collaboration with many customers that they are creating their camera for satellite tracking, star monitoring, and so on, but also for drone detection, visual odometry, and so on. But if you want to evaluate the technology, that's usually one of the problems that we saw in the past. You can also already buy an evaluation kit that is a very easy to use sensor. It's like this. It's a USB sensor that you can plug and play in your computer, and then you can use it. And now recently we announced also the possibility to buy the Gen 4, so the megapixel resolution sensor. That is something new. And recently again, we announced also our software. So you can download the software for free for evaluation, and you can play already with your sensor, with our sensor, using the framework that we implemented with all the Python binding and then C++ binding with PyTorch or TensorFlow, all the framework in machine learning that you want to use. And we also created a way to export the data from Python to MATLAB to work with MATLAB. It's an evolution of the software. Of course, it's growing in the market. We are following the requirement of the customer, and we will see. In February, we announced a very important collaboration with Sony. At the end of the year, Sony is going to mass production this megapixel sensor. The main advantage is that we have access to the new technology of Sony about the stacked pixel. And so we can improve the high dynamic range of the sensor and be more, we have a better fill factor, so a better sensitivity. And we reduced a lot of noise. And to give you an example, I show you a recording done here in Paris. It's funny because you can see the insect moving in front of the car. And you can see the quality of detail that you can achieve with our sensor, the megapixel sensor. So you have all the details, you can see better. You can also read the plate of the car if you want. And this sensor will be the future. So it will be the next generation of future of sensor. And in the end of the year, probably in 2021, 2022, Sony will start to produce and sell the sensor directly with our IP. Recently, we also announced the software. We have 3 different ways to use the software. One is very easy, that is just a software to plug and play the sensor, so you can use a recorder, record video, see the streaming of events, and so on. We have the designer. There are particularly the Python binding to help you to prototyping, fast prototyping the algorithm. And we have also the SDK in C++ that you can use a free license to do some testing. But if you want the code, you can buy the source code, and so you can compile with your platform if you want to use for Jetson, Xavier, or any kind of embedded device. My company is focusing on 3 markets now, as I say, industrial automation, robotics, mobile, Internet of Things, automotive. We have collaboration also in space, but we are not focusing on this market. For the moment, I are exploring more research projects, so I know there are a lot of collaboration. I will focus more on what we are doing now, and in case you are idea or you want to have more information about how to use the sensor in different applications, I will be available. You can contact me. The technology is more or less the same as introduced by innovation. So the idea is always the same. You have a matrix. Each pixel is asynchronous, and you react in an independent way to the change of illumination. And so there is, in particular, is the logarithmic of the illumination. So if the change of illumination is positive, you have positive events. If the change of illumination is negative, you have negative events. And this is the reason why you have this strange picture with the black and blue pixel. The black pixel are the negative events, and the blue are the positive events. Of course, we don't have frames. We have a stream of events. But to show you the video, what we did was to accumulate these events in a time interval and recreate a sort of frame and video to represent the event stream. It's important to say that we are very fast because we can detect event at the precision of microsecond. We are very robust to illumination change. We can reach 120 dB of high dynamic range. And we are also reducing the quantity of data because we can detect fast motion and focusing only on the dynamic of the scene. So we are only focusing on what is moving in the scene. Show you some application very quick, because in this way you can have an idea how we use the sensor with the customer. In particular, industrial automation, we have a strong collaboration with a German company called Imago that is commercializing the sensor in this industrial grade format. And it's used in different places in the industries. For example, one of the first applications was the high-speed counting. We don't have the problem of blur, so we can detect fast motion, and so we can detect a very fast motion without any kind of blur effect of error. And we can reach an equivalent of 10 kiloframe per second camera, reducing the quantity of data and detecting only what is needed. This is very important, especially if you want to acquire information without large exposition or affected by any kind of speed. And this is a product that is already on the market, that is already used by several customers in their production line. This is another nice application. This is arc welding monitoring. Here we are using both the high speed and the high dynamic range. Usually it's very difficult to find the point of soldering when you're closing the loop for this kind of application. With our system, we are very strong in high dynamic range, so we can detect the point of the soldering, close the loop, and do a control. And this is another customer that is using this kind of application in their production. And another nice application that we discussed also with people that are working on creating satellite is this vibration monitoring. The idea is that with our camera, we can see very fast motion. We have a precision of microseconds, so we can detect 10 kilohertz of frequencies. So you can analyze the dynamic of the mechanism. So you can analyze the movement of the scene and estimate independently the frequency for each part of the engine, and then create a sort of fingerprint that can be used to analyze the vibration of the system. This vibration is an information very useful because it can be used for machine learning to predict eventually some malfunctioning or to validate the good behavior of the engine. Another nice application that we worked a lot are the machine learning, and particularly the detection and tracking of different objects. Here I will show you what is I can show you for automotive because it's already well known. The idea is to use the event-based camera speed and robustness to illumination change to detect, for example, in this case, pedestrian or obstacle in less than 10 milliseconds to activate the brakes of the car. So in this application, we wanted to verify that it's possible to use the event stream, so the high temporal resolution, to detect with a machine learning system the presence of an object in front of the car in time to activate the brakes for safety. We did several tests in collaboration with Renault Nissan in this test site, where we tried with this kind of puppet mannequin to analyze the behavior of the sensor in different light conditions and with different speed, with different vehicle. And we created a first prototype of the product that now is in progress. It's in certification progress, because of course, when you are going on the automotive, you need to have the certification of safety before to go in the market. But the first results are very interesting. And starting with this data set, we started to create a framework for machine learning for detection and recognition and tracking. One of the problems of machine learning usually is that created the data set, because you can imagine with the frame-based camera, the problem is to create a ground truth, collect the data, create the labeling and classifying the object, and then training the network or any kind of a machine learning framework. So to simplify this process, the idea was to start to work on a hybrid solution where we are synchronizing and calibrating together a frame-based camera with an event-based camera and transfer the information between the two sensors in geometrical ways, so in a mathematical way. So it's quite good. So the idea is to calibrate the two systems, use the frame-based camera to label the object, classifying them, and also validating them. As you can imagine, it's easier to validate an object in the frames because you have the full picture that in the event stream. And then transfer this labeling from the frame to the events and do the sort of interpolation in time to cope with the hole between the frames. We create a huge data set. Most of the data set is available online, so you can already download it for free. You can try to do machine learning with this kind of data set. But recently, we announced we published a paper that is now accepted in Neuromorphic 2020, and we showed how to use neural network. In particularly, it's a recurrent neural network based on Convel STM that is showing that how to use this event stream to create a machine learning architecture that is able to do a classification of objects, in particular in this case, a car and pedestrian and two-wheeler, that is achieve the same results that you have with the frame-based camera. We compared the results, and we demonstrated in this paper that it's possible to achieve the same accuracy that you have with the frame-based camera by using the events, and so maintaining the temporal resolution and also the robustness of the events. And also another particular things is that you can reduce the quantity of the number of parameters of your network. So this is a very interesting result. We are very excited because it was accepted in Neuromorphic, and now we are going to publish the paper in the end of the year. To show you some preliminary results, this is a video we recorded from Always in Paris. You can see here the event stream. You can detect the car, and also you can do a sort of tracking of this car. This is you can also detect sometimes, I don't remember, this is just with the car, but you have also with the two-wheelers and with the pedestrian. So as you can see, it's very robust to the change of illumination. You have a robustness in the case of traffic and so on. And in particular, this system is quite interesting because it can be ported in a Qualcomm Snapdragon, so on an embedded device. It works very well. Why is important the event base? The event base is very important, especially when you have a very challenging light condition. For example, a low light condition. Here you have an example in comparison with an HDR OmniVision sensor that is used for a car. Usually in low light, what you are doing is you are combining different exposure picture to create a frame. But this is a problem when you have a fast object moving in front of the car. So if you see here, the car is on the top is moving, but you are not able to see the detail of the car. This is because the different exposition create a blur problem, and so you have this weird behavior. Instead, in the event-based camera, we are able to reconstruct. So we have all the details of the acquisition, and we can detect the shape of the car. And if you see also in details, it's quite amazing. You can also read the license plate of the car. So it's changing completely the possibility to use the sensor in different light condition and challenging condition. And if you compare the results with the frame-based camera, you can see that you can start to see something that usually when the frame-based camera is blinded. For example, the bicycle here passing in front of the car, or the pedestrian, the car on the background. It's very challenging for the frame-based camera, but for the event-based camera, it's easier to detect this object. Another nice application that I consider very important because we started to work in 2018 and now it's evolved. I will show you only the solution with the stereo solution, but we have a different approach with a hybrid sensor. I will work with this because we are going to present a new product at the beginning of the next year based on this stereo. The idea is to synchronize two event-based camera and use the temporal information to do triangulation. So if you synchronize the two camera and you calibrate geometrically the two camera, if in front of you you have an object that is moving the same speed and distance from the camera, you have the same events with the same timestamp. So you have two events with the same timestamp in the left and the right camera. So this means that if you can do the matching temporal using the time domain, and you can triangulate the information to do 3D reconstruction. In 2018, we did some experiment to try to do 6 degrees of freedom navigation. This is an example with the kitchen of my office. We tried to do localization using these 3D pinpoint clouds, and we created a system that is able to estimate the point clouds in 1 kilohertz. So it's quite fast. And so you can do data association easier. You can use the temporal resolution to solve the problem of data association easy. And we try, of course, in automotive also application. This is always in the street of Paris. You can see, even if you don't have a lot of parallax, you're able to see the motion of the car. And we have several data sets, we have several applications. And currently, we have also a live demo for this solution that is available. Okay, I was very fast. I tried to cover more or less everything. The main important thing is that with event-based camera, we are very fast. We see only the dynamic of the scene, so we can compress the data a lot, especially compared with the frame-based camera. Imagine if you have a high-speed frame-based camera, you can have a huge amount of data. Instead, with the event-based camera, you're focusing only on the moving object. We have a robustness in the change of illumination, and also we have a very competitive power consumption, so this become interesting. We have several applications. I covered just a few because many applications are covered by NDA, but many applications probably are too far from the application space. We have a collaboration with university working on satellite tracking, also with company. And we see there is a big trend of this topic. Of course, is not part of our business, but if you're interested to evaluate the technology for your research, contact me and then we can discuss. So this is my reference. You can run me, and if you want to have more information, you can download the white paper from our webpage.
Thank you very much, Davide, for that. I don't see any questions. So I think we can now move on to our final speaker, Dylan Muir from Simpsons, which is also based in Zurich. And Dylan is Director of Global Business Development at Simpsons. We are now going to move on from talking about sensors to talking about the neuromorphic processing units and how, for example, the data produced by neuromorphic sensors can then be efficiently processed in a low power and high latency manner. Please, Dylan.
Thanks a lot, Andrzej. Yeah, thanks for setting up this small workshop. And thanks also to Kynand and Davide for setting the scene up for event-based processing. So let me just share my slides here if I can. Okay. So I work for Synsense. We're a startup based in Zurich, as Andres mentioned, and our focus is on low power real-time processing, signal processing in an event-based way. So I'm the director of the algorithms and applications team at Synsense, as well as director of business development. So my team is sort of a researchy team where we build applications and solutions to use the low power technology that the company produces. My background is in computational neuroscience, originally modeling biological neural networks. And originally in ancient history, it was electronic engineering and computer science. So we are based in Zurich. We were founded at the end of 2017. We're expanding this year into China. And the focus of the company is to design custom silicon ASICs for ultra low power signal processing and machine learning inference. So we want to use our technology, our hardware, to enable what's called edge processing, in continuous real-time mode at extremely low power levels. So by edge, what I mean is things like smart home devices, mobile phone handsets, Internet of Things devices, things like this, where usually you would not be tethered to a power cable, so you have some power constraints. But essentially, any application where data transmission is too expensive or is somehow undesired in some way. So you have a need to do processing, signal processing or machine learning inference locally on the device, and that's what we enable. When I say low power, I mean in the order of a milliwatt or less than a milliwatt. The way we achieve our low power computation is by using a special computational substrate. So we have two lines of hardware. One is designed for vision processing, which I'll go into a bit more detail later on. One is designed for what we call low dimensionality signal processing, which would mean things like real-time audio processing or vibration processing, health signal, biosignal monitoring, things like this, any low dimensional real-time signal. And the computational substrate that we have in all of these chips is based on asynchronous parallel processing of events, of real-time events, of the form, for example, that are produced by the dynamic vision sensor cameras that Kainan and Davide just presented. So to give you a little bit of a technical understanding of the underpinnings of the way our hardware works, I just want to go through a couple of slides here about contrasting standard neural networks with spiking neural networks. So our computational substrate based on asynchronous event-based processing, sometimes referred to as spiking neural networks. You're probably already all familiar with standard artificial neural networks, which are essentially little chunks of matrix multiplication, followed by summation and some basic nonlinear transfer function. In these units, if this is a single neuron, we have a vector of inputs, which are usually real valued numbers. We have some input weights for each of these input values, which are then summed inside the neuron and passed through, along with a bias input, and passed through a nonlinearity to produce some real valued output. I say these values are usually real valued numbers. Of course, there have been lots of advances in recent years to reduce the precision requirements of these systems by quantizing weights, by quantizing neuron activations. And the way that these artificial neural networks are structured, systems such as GPUs and TPUs, tensor processing units, vector processing units, are able to very efficiently evaluate these systems. So the computational units that we use are called spiking neurons. And the main difference between spiking neurons and artificial neurons is the introduction of time and internal state. So I've highlighted here this time element. The signals inside this unit, this neuron, are a function of time. and there is some internal state that is maintained by the neuron, which evolves over time. But again, basically, you have some input signal, some internal state, a transfer function, you produce some output signal. Now the internal neuron model is slightly more complex. The input signals are these discrete single-bit binary events, which are integrated within the neuron, combined with the neuron's internal state, and combined with a threshold on this neuron state, then the output signals from this spiking neuron are again discrete binary, single-bit binary events that occur in real time. And both these input events and output events are identical in flavor to the events that you saw from the event vision cameras from Kynan and Davide. So if you squint at these two neuron models, you can see that they're not so dissimilar. They both integrate some inputs, they perform a summation, they produce an output which depends on magnitude of the input. We have some hardware which implements these types of spiking neurons with complex internal dynamics directly using the physics of the silicon. This makes them extremely power efficient. We also have hardware which implements a digital version of these spiking neurons, which is what I'm giving you an overview of here. So these neurons are very simple. The internal state is a binary counter. The weights are binary values. The input synaptic events, again, are single bit binary values. When the internal neuron state crosses a threshold, then it produces a single output event, a single bit output event. So this is a quantized version, a discrete state version of the continuous spiking neuron. But the important thing to note here is that the computation in this neuron can be strictly event-driven. So we don't have a continuously running clock in any of our hardware. We have fully asynchronous hardware. We only perform any computation when we receive an input event. There's a couple of benefits that we get from using spiking neurons over using standard artificial neurons. And the first is that if the input information is sparse in time, then we can achieve very low power consumption by not performing any computation. As I mentioned, we only perform computation when an input event passes through a neuron, passes through the network. So as a result of this, if there are no input events or a very sparse input event rate, then we simply don't perform any computation. And this is in contrast to standard frame-based image processing, where you have to perform the same computation on every single frame, regardless of how much has changed between one frame and the next, for example, for a vision processing application. The second main advantage of using a spiking neuron as opposed to an artificial neuron is that time is an inherent part of this computational substrate. The network and the computational units intrinsically understand time as a core part of the computation. Standard artificial neural networks do not have any implicit representation of time. You have to jump through a couple of hoops to unroll time, to include time as part of the network itself. So if you're using spiking neurons, processing temporal signals that evolve over time is a little bit more natural and fits a bit better with the computational substrate. So we design custom chips that perform inference using these spiking neural networks, and are designed to do so using as little energy as possible. We have two lines of hardware, as I mentioned, one for low dimensional signal processing. Audio, for example, I just want to very quickly run through an example of a low dimensional application, in this case, audio processing. And then I'll skip through to the vision processing, which is potentially of greater interest to the attendees today. So this is a real-time audio processing example. The network should identify spoken key phrases, so a wake phrase and several command phrases. It should do this in real time with low latency and low power. What you see here is an overview of the network architecture that we use for this sort of application. We have the raw audio input coming in on the left. This is passing through a bandpass filter bank. spanning a range of frequencies which are appropriate for spoken audio, for voice. And this filter bank produces series of events at the output of each channel, where the events encode the power in that frequency band. These events are processed by a recurrent network of around 1,000 low power spiking neurons. And the purpose of this recurrent network is to project the input signal into a high dimensional space, and also to mix the temporal components of the signal over time. So these spiking neurons have a range of internal time constants in the way that they respond to input events. And so this recurrent network provides a high dimensional complex temporal basis which you can use to analyze the input signals. So as a result, we can train the network with, in a machine learning sense, in a supervised training sense, to have a number of outputs where each output recognizes a particular sequence of the input signal, in this case, a spoken key phrase. Here is a demo of this network running in real time. I'm not sure if you'll be able to hear the audio or not. We can give it a go. The top signal is the raw audio input. The next signal down will be the activity of the individual filter banks. You can see the frequency components of the signal. In the middle indicates the state of the network, which will shift from sleeping to awake when it hears the key phrase, the wake phrase, which for this network is the word Marvin. And then the network will listen to a number of command signals, stop, go, left, and right. The next signal down will indicate the output, the detection output of the network. And at the bottom is a real-time estimation of the energy consumption in microwatts. So I'll play this and hopefully you can see the animation. Let me try that again. The animation didn't seem to work there, although I could hear the audio. Okay. So I'm not sure if you could hear the audio or not. Andrej, can you tell me?
No, I couldn't hear it.
Okay.
I could just see the animation.
No problem. So you'll have to imagine someone saying Marvin in a German accent, or stop, let go, left, right for each of these little bumps of the audio signal here. But you can see that the response of the network is essentially on the time scale of the audio signal itself. So when Marvin is spoken, then the detection output of the network the latency is essentially real time, so less than 100 milliseconds. And the computation in the network is happening continuously. You might have noticed that this power consumption graph down the bottom is not constant. In fact, there are peaks. It maxes out here at around 15 microwatts. And this is modulated by the activity, the input events passing into the network. So when there's spoken audio, there is a higher rate of input events, there's more computation taking place in the network, and therefore there's more power being consumed. So we can train a network like this for real-time low-dimensional signal processing with low latency and high accuracy. And then for power consumption, we're looking at a total power consumption of less than 200 microwatts. Okay, so in the context of the low power vision sensors that Kainan and Davide presented, I want to give you an overview of our technology for low power vision processing. We have a set of processors that we've designed in the company and prototyped over the last year, which are specifically designed for convolutional neural networks, but operating in a fully event-driven asynchronous mode. So you're probably possibly all aware of what convolutional neural networks are and what they're used for. This is the standard way of performing vision processing in 2020. I would say that that's a fairly non-controversial statement. So our hardware is able to simulate these convolutional neural networks. It's a fully digital architecture, fully asynchronous, and it's reconfigurable to the extent that you have a number of convolutional layers which you can connect in any way you choose, and each of the layers can be configured to change the kernel sizes, the feature sizes, the numbers of features, and so on. And the computation inside this hardware is, as I said, fully event-driven. So although you can send any event source technically and into these convolutional processing cores, they're designed to be used seamlessly with the DVS event cameras that Kainan and Davide presented in the last two presentations. So what I'm showing on the left here is events from a DVS input array, which would then pass through a number of convolutional dense layers operated in inference mode, and then the result of this convolutional neural network would be computed by our chip. So I'm going to show you two applications that are running on our hardware, on our prototype hardware. The first is a face detection applications. So I want to apologize. I don't have any space applications to show you. We've been focusing mostly in the last couple of years on consumer applications. So I don't have space applications to demonstrate to you today. But I want to show a couple of different applications that give you a sense of what flavor of signal processing we can perform. So the first here is a face detection application. What you see here is the convolutional architecture that we are using. It's a fairly standard CNN architecture. It's not very large. Technically, we can use, we make use of some pooling between layers. We train this network by training a standard non-spiking convolutional neural network using industry standard tools, using input data, which is a representation of the DVS recorded events. And then we can convert this standard convolutional neural network into an event-driven mode, which is identically compatible with the digital hardware architecture that we have. And then we can deploy that directly from our open source Python libraries onto the prototype development hardware that we have. So what I'm showing you here is, I'll show you a demo of this application running in real time on our hardware. What you'll see here is a standard CMOS camera overview of what's going on. What this little red camera here is in fact a DVS camera from Innovation, and it's connected to our development kit hardware. What you see on the screen here, which is copied on the right-hand side of the image, is the real-time output of the DVS camera and also the real-time detection output of the network. So you'll see face and a picture of a face appear here when a face is detected by the network. And so the task the network has been trained to perform is to detect when a face is present looking at the camera and to ignore other inputs, so a waving hand or the back of someone's head or some background motion. And you can imagine this application being deployed on a mobile phone handset where the handset should wake when it detects that someone is looking directly at the handset. So I'll play this. Okay, so first you'll see our engineer Tien waving at the camera. Nothing is detected. And when she places her face in front of the camera, then the network correctly detects that a face is present. When she shows the back of her head, then the network ignores this. She'll detach the camera and demonstrate that even in the case of motion, so background motion or a background theme, then the network does not detect faces. So we have what you expect for CNN level visual selectivity running in a purely event-driven mode. So here we've had to visualize the DVS frames, DVS output as frames, but this is strictly for visualization purposes. And of course, Kainan and Davide had to do the same during their demos. That you have to, since we're looking at the world through a frame-based representation, we have to render things as frames. But the hardware itself is fully asynchronous and handles the individual events passing from the DVS cameras one by one. So the second demo I want to show you is a real-time gesture detection demo. So a similar sort of setup here. You can't actually see the DVS camera, but you can see the leg of the tripod here. And static will perform a series of gestures. You'll see the real-time DVS output, and you'll also see the gesture detection and recognition readout on the bottom right of the screen. So air drums, clapping, left hand waving, as well as right hand waving, air guitar, this strange hand roll gesture, and air guitar again. Right, so the reason why we're able to get such, okay, so I should say both of these, I don't have a real-time power estimation here for these demos, but both of these demos are running at around a milliwatt average power. The reason why we can perform this inference at such low power is because of the asynchronous nature of our hardware. So if you imagine the architecture here, we have single events coming in. We can get away with a simpler architecture because we're dealing with single events and not frames. A standard convolutional neural network receives an entire frame and then perhaps has to perform some fairly large matrix multiplications and accumulations. And that using a GPU or TPU, you try to do this as efficiently as possible, but multiply accumulates are the name of the game for standard CNN inference. We can get away with just doing summation. We don't need to do multiplications. And the reason we can get away with that is because we handle these events asynchronously and natively as single events. So when a single event comes in here, you can imagine all we need to do is take the single kernel that's located at the pixel where that event occurs and sum that weight pattern onto the next layer. And because each event implicitly has a value of 1, multiplying by 1, you don't need to do the multiplication at all. So we can get away without multiply accumulate and simply do the summation, simply do accumulations. This means that our inference hardware can be more compact, can be simpler, the circuits can be simpler, and then therefore we save space and therefore also save power. So here's an overview of our prototype development board, which both of these two demos that I showed you were running on. We are planning to make this available towards the end of this year. So as a hardware development kit, we have software development kits already available, these as open source Python packages. These are available from our website. And so if you're interested in trying to see what you can do in event mode for event-based vision, then you can try yourself already at simulation. And if you would like to acquire one of these development kits from us early next year, then you can also test these out in hardware. So the important take-home messages here are that everything I've showed you is vision processing based on fairly standard convolutional architectures. So if you can train a convolutional architecture to perform your application, no matter what that is, then you can deploy that on our hardware. And so there's an almost infinite array of visual processing applications that currently exist in the world that are all deployed on CNNs. The reason why I wanted to show you these two particular applications is because they cover two sort of slightly different modes of input data. So the first face detection algorithm was something you could imagine taking place fairly easily with a frame-based camera. You don't need to analyze the temporal component of the input signal in order to perform that application. However, the gesture recognition application is one where you taking the input signal inherently as a temporal component, and so being able to take into account and analyze that temporal component gives you some extra benefits of using an event-driven convolutional architecture. So the take-home message is really that the low-power real-time applications is where our hardware shines the most. If you have tens of watts or hundreds of watts to burn, then you can call up NVIDIA, call up Qualcomm. But if you want to be measuring things in microwatts or milliwatts, if that's more to your liking, then maybe you should keep us in mind and keep our hardware in mind. And yeah, with that, I'd like to thank you again for the chance to give you an overview of our technology. And I'm very interested to hear what use cases you can think of that could make use of our technology and these sorts of cameras, these sorts of vision processing.
Thank you very much for that, Dylan. Right, so that concludes the part where we have the talks from the invited speakers. I do not see any questions from the audience. However, I do have questions to the speakers, so we can just move to them. So my first question is to Kainan, and this is a question about the partnership with Samsung, because from what I know, Samsung has quite recently released their own DVS camera. So I was wondering if that camera uses Davis technology. Was it developed in a partnership with any labs, or is the partnership formed after that?
Yeah, that's a complicated question. Let's say that we've known them for over 10 years, and we have partnerships on different levels. I'm not sure which chip you're talking about exactly. If you're talking about the one that was in their IoT product, right, the private surveillance.
Yes.
Product. Yeah. So that's one that they developed themselves based on the original IP.
Okay. Thank you for that. Next question I have for Davide. And this is a question about the video that you've shown us with the car detection using the DVS data. So do I understand correctly that essentially what you do, you synchronize the DVS sensor with a frame-based cameras to collect the data, then you create ground truth manually, or do you use some sort of other network to create pseudo ground truth?
So, okay, first of all, I would like to correct something, because DVS is a trademark of Samsung, so we cannot use it for the camera, our camera. So pay attention, because for me it's a problem, because I cannot talk about DVS, and I call it just event-based camera. And secondly, yes. So currently the idea is this one. We did something very simple to run a state-of-the-art machine learning camera and car detection, pedestrian detection on the frame base. We collect the label, we correct the label manually. So in this way, you have a first classification. You correct it with the ground truth. Then we created the ground truth, and we do the interpolation in time to have the time resolution of our event-based camera. And then we do the training. So in this way, the detection is done at the millisecond precision. As I said before, we are able to detect a pedestrian in 10 milliseconds. So in this case, we tuned the network in different way. In particular, we considered the time interval of 10 milliseconds in our experiment to do some evaluation. And you are able to do the classification correctly. So the ground truth, you have the synchronization, the calibration with the frame-based camera. You transfer the label from frame to events. Then you do the training with the resolution of the event base. And then in detection, so when you have inference, you are doing the inference at the resolution of the events.
Okay, thank you for that.
If you want information, there is the paper I cited, how to train 1 megapixel, how to use, I don't remember.
From Neurips, yes.
Neurips, it's already available in archive. It will be published at the end of the year.
Okay, thank you for that. Right, and the next question I have for Dylan, and this is about the training and the inference, because from what I understand, you do not do any training on the chip. Is that because it's just because this transfer learning works nicely, or because the training on your chip is just inherently impossible?
So our hardware is not designed to support training directly on the hardware. And the reason for that is we want to use standard machine learning training pipelines. So we want to use backpropagation of gradients through the network to perform training. But the problem with backpropagation is it requires maintaining a large amount of state during backpropagation. And so if you want to build an ASIC that supports inference and training, you have to essentially build a large extra structure to handle that backpropagation-based training. And so it's much, much more efficient to just build hardware that performs inference. Because we're targeting low power applications, training is not the perfect fit, because training takes a long time. Time means power. Training requires a large amount of data for standard machine learning pipelines, and you need to have good data engineering. And so I can't really imagine a good use case for us where you deploy a chip that has training on a consumer device, for example. So you don't have control of the data, and a consumer doesn't want to spend a long time training the device. However, so for that reason, we've designed the hardware for inference. The transfer learning does work well. Since we can easily run a simulation of our hardware architecture, we can perform all the backpropagation using our hardware architecture and simulation. We don't need to use the hardware for that. Then we can deploy it onto the hardware, and we know that it will work. Having said that, the hardware itself is reconfigurable, as I mentioned. So you can modify a network and deploy it onto the hardware. You can easily reconfigure the hardware. So you could imagine a scenario where you have training with our hardware in the loop. And so you could run inference on the hardware, maintain some training model, and then redeploy onto the hardware. You could imagine a use case where you just perform training on the last layer or the last couple of layers of the network. And this is done quite commonly in industry, where you have a large pre-trained network, and then you train just the last layer or two in order to specialize that network for your particular application. And this would work well with our hardware. So you could have a pre-trained vision processing network on our hardware running in inference, and just modify the last layer for detection of a particular event, for example.
Okay, thank you. So the reason why I ask about this, because I can actually see an application where you would need to perform the training on a chip. And this would be in particular an Earth observation, where you put the sensor and the processing chip on the orbit at the same time. Obviously, having two missions to collect the data and another one to do the processing is financially unviable, I think. So, and we don't know what, say, this DBS data, which is collected on a remote sensor on a satellite, would be like. So we cannot really create it synthetically. So in that sense, I think it would actually make sense to be able to have the ability to perform the training on the edge.
Mm-hmm. Yeah, I can see that. And as for any machine learning application, having a good data set is crucial. And as you point out, if you're deploying a DBS camera in space for Earth observation for the very first time, it's very hard to know exactly what the quirks of that data set will be. So I can appreciate that. Yeah, probably you could perform training in the loop, as I described, using you'd need to have an additional system processor, so you could deploy the satellite, perform training, and then switch off the training loop and run in inference mode to reduce power consumption. You could probably also pre-configure the network, at least the first couple of layers of the network, which for many CNN architectures, the first couple of layers end up having very similar structure, very common structure for visual processing. You could pre-configure that and then just train maybe the subsequent 5 or 7 layers, something like this. It might make things a little bit cheaper. But yes, I can see that would be a requirement.
Okay, thank you for that. Well, I hope this session was quite illuminating to all the participants, because probably most of the participants today had no previous exposure either to neuromorphic processing or neuromorphic sensing. So it's not only you who do not know particular space or Earth observation applications, but the participants probably did not consider this technology before. So the hope is that this may start some sort of considerations of how this technology can be used for Earth observation in the future. And the particular application that I do have in mind, although it's quite elementary at this time, is things like, for example, wind speed estimation, or which is used to say classify hurricanes and their strength. And for that, for what's happening now, for that we do use a sequence of subsequent frames to see how, say, a hurricane evolves. I think with technology like DVS, it couldn't be done much more accurately. Because we could see that evolution, as you say, on a level of microseconds, and then being able to process it while on orbit would also be something which is quite impressive.
Maybe I can make
Class?
one comment. Sorry.
Yes.
Yeah, I could make one comment on that. I mean, of course, we've never done that particular use case, but what has been done is particle image velocimetry in a lab situation, 3D particle tracking. So we know this is, at least in principle, possible.
Yes, so it might actually be an interesting, viable project. As for the processing on the orbit, I've mentioned to all of you the Phi-sat, and I actually have this. Sorry, I'm not sure you can see me. I've got this Movidius computer chip that has been put on the orbit, and just to give some idea to the participants how they compare. So this uses about a milliwatt on average while it processes the data. And when we speak about, sorry, a watt, a single watt when it does the processing. So when we're speaking on a range of being able to work in a milliwatts, this is a 1,000-fold improvement, which is just amazing. Right. So that is all from me. If there are no questions from the audience, I'm going to conclude this session by thanking again the speakers for these presentations. Thank you very much. And thank you to all the participants for participating in this one of the last sessions of the Phi-Week. Thank you.
Thank you. Bye.
Thanks, everyone.
Thanks very much.
Thanks, Andres.
Thank you. Bye.
Thanks. Bye.